Okay. I started recording now. But thanks for the reminder. Okay. At least my watch is, of course, maybe not correct, and I don't see the clock on here. But maybe let's get started. I think you remember my face. This afternoon, you're going to see Alex's face here in front because he's giving the 4th lecture of our little lecture series on atom. Maybe yeah, there you go. Okay, on atom interferometry. So just a quick recap, what did we do yesterday? Yesterday, we talked a little bit about atom optics, and that's, of course, a little bit overselling it. We did atom diffraction with single photon or clock transitions and described that how those transfer momentum. The second lecture yesterday afternoon was on the structure of atom interferometers. Today, we will talk about basic examples, and I will discuss also the sensitivity from a, let's say, single particle point of view. Very easy, but that's, I think, the beauty of it. And then Alex will talk about perturbations and different interferometer branches later on. What did we do yesterday? We were talking about pulse sequences, so having a Mach-10 interferometer, but of course, everything we're doing here can be generalized. And what you will learn is that actually you don't need to apply all those matrices as we did yesterday, because you do it once and then you understand the principle and then you're fine. So the way I always work with atom interferometers, I just draw the interferometer that I want to do, and I just think in terms of the external motion and then just add the internal degrees of freedom by that. So we have a Mach-10 configuration, but in principle, we could generalize that, having a pi-half pulse, waiting for time capital T, a pi pulse that redirects both arms or branches, and then waiting again for another time or looking at the time evolution in an external potential. And we want to learn something about this external potential. And then, of course, mixing those two arms so that we cannot distinguish the two. We saw, and so this period of time actually may be different, and I will discuss this difference because that's kind of important. We can describe now the evolution along each branch just by the center of mass motion, just talking about an increased kinetic energy followed by a time evolution with a decreased kinetic energy for the upper arm, and a time evolution with a lower kinetic energy first, and then followed by a time evolution with an increased kinetic energy. What I didn't do yesterday, and I actually should have done that and wanted to do it, but I didn't do it, there's also these global phases that I just pulled out. And they include the following, just to remind ourselves what they did. They were including now here these phases, and they depended on the internal energies as well as the laser phases. And I wrote it down here again, what we had yesterday. That's something that you've seen for the first time, but I wanted to do that. This is the laser phase difference that we are observing. So it's the phase of the final pulse minus 2 times the phase of the mirror pulse plus the laser phase of the first pulse. And then on top, if you just take the difference between those phases, you see that there is a clock phase arising. And it depends on the atomic frequency, so the transition frequency times the difference in the time evolution. So one time evolution is capital T, and the other one is capital T plus delta T. And this delta T is a measure for the time that the atom spends in different internal states. And of course, if you were to build just a Ramsey clock, this clock phase would be the thing that you're measuring. Of course, when we are building an atom interferometer, we are not interested in generating a frequency difference, so that's a reference, so that's not what we're building. But in principle, we are also susceptible to those clock phases. And we will see this when I talk about my first example, which I'm doing right now. So the first example that we're talking about, so I also wrote down those, we are interested now in this overlap operator, so U1 times U2 dagger. And this is just the sequence of those operators that I have to now to just calculate. You could do that. I mean, this describes the overlap of two wave functions just propagated along those two arms. But you could do that, of course, any way you want to. But I will calculate that in an operator form, because you also see that now accelerations generate phases. So what we look at the first example, that's the a closed interferometer with free atoms. Okay, and I will zoom in to make it larger. So just to not have any potential or something like that, just understand, no, that's a closed interferometer, just understand what's happening. So what we're choosing for a closed interferometer is effectively saying that this delta t is equal to 0, so that both time evolutions happen for the same period of time. So what we choose is delta t is equal to 0, and that implies that both arms, both branches, cross exactly at the final beam splitter. So in fact, I now have again these position and time diagrams, and I have one arm, and I think the upper arm was green, so this would be the upper arm, and the lower arm would be coming here, starting at the same point, going straight, then inserting momentum, and then being exactly at the same point, because those laser pulses are now equally separated, of course, modulo my shitty drawing. Now, what is the Hamiltonian? We are not discussing any potential. So the Hamiltonian is for a free particle is very easy. So it doesn't really depend on any potential. It's just p squared. So h external is p squared over 2m. Just yes.
Since no one is asking questions, I will do that.
Yes.
So please do ask questions. Unfettered. I mean, yeah. Beforehand, you draw your diagram kind of differently. The blue lines were all slanted, and the green lines were all horizontal.
Yeah. So what I did before, now we basically switch gears. So at first, I just always said, okay, I have entanglement between internal and external degrees of freedom, and so on. What we did now, we calculated the matrix element for going in one particular exit port with the ground state and coming out of the interferometer in the ground state going straight. Now, we basically focus on those matrix element and just calculate the center of mass motion. From now on, I cannot really talk about different internal states anymore. Now I just do talk about the time evolution along those two arms. So I switch from saying, okay, I have a general system and entanglement to I have two arms, I have a unitary time evolution along each arms, and I'm just worried about the center of mass motion along these two arms. And that's why U1 and U2, they describe those two motions, and that's why I do have different colors for those two different arms.
These are the two different paths that interfere later.
And they will now interfere, exactly. And that's what we're going to see. Okay, that's something because I didn't. So in principle, we will see that. But if you think about that, think about Heisenberg's equation of motion or something like that. And if you just do a calculation of those Heisenberg equations of motion or classical trajectories, you will see that they will perfectly be at the same position. However, we will see later on what happens if you displace that and they don't perfectly overlap. We will see that in an operator structure. But if you were to calculate classical trajectories, they would also perfectly overlap. But we will see this in this scalar product in this operator as well. No, so we have, I'm sorry, we have again a beam splitter. mirror and a beam splitter, and they are separated by T. And so just, and this is just a one-dimensional thing. So atoms are here. Can you see that? Beam splitter implies 50% of the atoms or whatever, superposition. They get a momentum, so they go up here for a specific time. Then I make a mirror, so they stop up here, and I give a kick to those down here. And then I wait for exactly the same time evolution so that they're at the same position. And then I make my beam splitter. And so that's just by my hands, you should see that they overlap perfectly. Okay, so the cool part now is this Hamiltonian is independent of position. So effectively, the Hamiltonian commutes with a Hamiltonian of increased kinetic energy. So that means since we have the commutator of H external of depending on P and H external depending on P plus H bar K vanishes, I can just merge in this overlap that we are interested in. I can just merge everything into one exponential. Becker-Campbell-Hausdorff is trivia. So that means I can now write everything as U2 dagger times U1. That's what we're interested in. And it is, so first of all, because delta T is equal 0, I also see that phi 2 minus phi 1 is just the laser phase difference that I introduced. So it would be e to the I delta phi. And now I have the exponential, and I can just write all those different time evolutions in one exponential. So I write it as I over h bar, and I have the backwards propagation of p squared over 2m. Then I have the backwards propagation of the excited state that implies an increased momentum, p squared plus 2m. That would be the blue arm backwards. And now I go along the green arm in forward direction, so I get a minus sign. And I first have p squared over 2m. And then I have minus p squared plus h bar k. I'm sorry, of course the squared is up here. So increased momentum divided by 2m. And when you look at that, everything drops out. So what you see now is that this overlap operator is e to the I delta phi times the identity of the external degrees of freedom. And everything drops out because the interferometer is closing. We don't have any operator left. That's just the identity. So now it's actually very, this is now perfect overlap. And a closed AI. So it is also very easy now for this type of operator for any input wave function, center of mass input function, to calculate the expectation value. That is, I just calculate psi naught, and this was, what was left that we had to do. Psi naught is equal times U2 dagger, U1 times psi naught. And that is just e to the I delta phi, psi naught, identity of the center of mass motion, psi naught. Of course, that is just e to the I delta phi. And so we now see that the visibility, the modulus of this overlap operator is equal to 1. And we observe the interference signal. I call that IG yesterday. And that was 1/2, 1 plus cosine delta phi. So we are just measuring the laser phase difference of those 3 lasers, this 3-point laser phase difference. And that's it. And the visibility is perfect. And we measure the laser phase. So we see visibility, that was the modulus, is equal to 1, and laser phase phi is equal to delta phi, which is phi 2 minus 2 times phi 1 plus phi naught. Okay, so far, yes. I'm sorry. External. It's always like the external, the center of mass motion. Yes. Because I just calculated. So what we had was usually this yesterday. We saw that this the interference signal, when we calculated it here, we had 1 plus visibility cosine phi, and this visibility was defined as the modulus of the overlap operator. Where did I define that? Yeah, so this is the overlap operator, and I said here the overlap operator is its modulus and phase, and the modulus determines the visibility. And now, because the overlap operator is unit operator, identity, we just observe that it is equal to 1. Okay, so, and actually I will call everything where you have up to a phase an overlap operator up to a phase, I will always call that a closed interferometer. Yes. I'm sorry?
So there you write your external of T and B.
Yes.
And now we're in H. So,
yeah, so I calculate, but I'm sorry, I also didn't specify that. We have a time-independent potential. So U external of T is equal to E to the minus I over H bar H external times T. And so, because everything commutes, because I don't have any position, I can just merge all those exponentials, and that's what I did in that line up there. That's what I did up here. So now, this is the first one, P squared over 2m. That's this U dagger here. Then I have P plus H bar K squared over 2m. That's this guy. And then I have it in the reverse order with a different sign. And everything drops out. And that's just because the time evolution, because the wave packets evolve exactly the same and they overlap perfectly. There should be, of course, and that's why I didn't close the brackets, there should be a T. And that's, yes. No, I mean that it physically in position overlaps perfectly, both wave packets. That's the condition. Yes. But we will now do an example where wave packets don't perfectly overlap anymore. And that is the open interferometer. And for that, of course, we still have the same Hamiltonian, so that's great. But we now open the interferometer. And we are going to do that by just choosing delta t not equal to 0. Okay? How would that look like? And I, again, draw a figure here of in space and time. So this is time. No, this is space. This is time, t. And now what we observe is that we have, one pulse here, and one pulse here. So it's displaced. And we now observe the upper path that goes up here and interacts. And we have the blue path, starts at the same point, goes straight, goes up, and then goes straight. And you see already here that there is a displacement between the two. And it's just because of this timing asymmetry. And so we can now, again, because everything commutes with each other, we can just merge all those time evolution operators into one. However, you know, for capital T, in the second period, we already calculated that. So the only difference will be the differential time evolution, delta T. Yes?
It seems like there should be another branch coming out of the green one, or is it just very exaggerated for the example?
This is actually describing these unitary evolution operators that go straight. I'm only interested, so we project it on one particular exit port, and that's what we define the interference signal. So we will only observe everything that goes straight.
Okay, but, so
okay, good. Okay, so it's easy to calculate again. So what we do is now U2 dagger U1 is equal to now e to the I delta phi plus omega atom times delta t. This is now the clock phase and the laser phase. And why do we now observe a clock phase? Because the atom has spent a different amount of time in different internal states. That's just coming from that. On top of that, we now have the exponential. And the remaining part is that we have, oh, this is plus I over h bar, is that we are having the Hamiltonian of P plus h bar k on one arm, external, minus h of P, h external, I'm always forgetting that, times delta t. This is, everything else is as before, everything drops out. And so now the time evolution for this little contribution after for delta t, so basically for this time here, this is the only thing that remains. So this is these two guys times delta t, their difference. So this is what we have to calculate. Did you understand that? Okay, good. Okay, so what we have to calculate, and actually we already calculated that when we were talking about resonance conditions. What we see now is in this case that we are having h external p plus h bar k minus h external p is equal to, well, it's p squared plus h bar k, so it's p squared over 2m plus p times k over m plus h bar squared k squared over 2m minus p squared over 2m. So this actually is now the kinetic energy difference between the two of them. Actually, this contribution and this contribution cancels. And what we now do observe is a difference that is p times k over m. That is the Doppler detuning plus h bar. I'm sorry, I'm missing an h bar here. H bar times k, h bar k squared over 2m, which is the recoil frequency. Now, the problem is, now we see that this overlap operator is not unity anymore, not identity, but we get a remaining momentum operator in here. So what we observe is that the overlap operator takes the form U2 dagger U1 is equal to e to the I delta phi plus omega atom plus omega k times delta t. Okay, I'm sorry, I did not define this. This here is nu k. We had that h bar nu k of p. That's the Doppler detuning plus h bar omega k, which is the recoil frequency. And so we effectively get a Doppler detuning at the very end of our interferometer. I p times k over m times delta t. And now this is not the identity anymore, and we will not observe perfect overlap. Actually, just as a, let's say, side remark, this here is a displacement operator in position. So if I have e to the minus I p k, a p, let's say, call it a position delta zeta over h bar acting on the position, this is this calculation actually follows exactly what we did for the momentum operator, just, you know, for position, this momentum kicks that we discussed. This is now a position kick. So it will just kick my position by z plus zeta. So actually, what we observe now in position representation, so this here effectively now describes the displacement in position. And I call that displacement delta zeta, and that would be the displacement in position that you observe here. That's corresponds exactly to that displacement up there. And so when we now calculate the scalar product in position representation, we won't do that, but it could be done. Yes. Yes. Yeah, that's just the laser phase. Yes. Yeah, so it's just because, you know, I have here now, I have now these exponential, and I have I over h bar, and I first have I of course need to get it right now. So it would be h of p times t plus h of p plus h bar k times t plus delta t minus h, okay, yeah, exactly, minus h of p times t plus delta t minus h of p plus h bar k times t plus delta t. And then closing everything that's in there. And when you look at that, that's just the time evolution operators, and almost everything drops out because this guy here and this guy here is the same. And then you see that this time times p plus h bar k minus uppercase t times p plus h bar k. So I'm canceling the one. This here cancels. And the only remaining part is proportional to delta t. And that's what's remaining up there, and that's what I calculated. Okay, good. So now let's calculate this overlap operator, the expectation value in position representation. So I now define just the position wave function, so center of mass wave function in position representation. There is a what? Oh, the last delta t is wrong. Yeah, exactly. Sorry. Yeah, exactly. That's wrong. The first period, that's the evolution along the green path, and of course that's just for a capital T. Yes.
Is there sign error because in the line that is like yellow, in front of the I is there a minus?
No.
Okay, there's no. Okay.
No, because you have backwards propagation, and then you have minus h, and that's the forward propagation in time. That's the dagger, effectively. So in position representation, we just define the position z acting on psi naught. That's psi naught of z. We just can calculate this expectation value, and that is psi naught times e to the I p times k times delta t divided by m psi naught, and we can just calculate this by calculating the scalar product of dz psi naught star of z times psi naught of z plus delta zeta. And delta zeta in this case is equal to h bar k times delta t over m, which is the different velocity times the timing asymmetry. And this is how those two wave packets are displaced now. And you can now take your initial wave function, displace it, overlap it, and calculate what's coming out. Yes? And yeah, but the point is, if this cat acts from the left, and that's what you would have to do. I introduced just the identity in between. It acts as a shift in positive direction, so it's correct. Yeah. Okay, good. So of course that's when you know this displacement operator, but maybe let's just calculate everything in momentum space, because it really doesn't matter in which space we work in. And so we do the same thing, and there it's getting easier. In momentum representation, where we now define now psi of p, psi naught of p is equal to p times psi naught. And what we observe now here is just having, psi naught e to the I p times k times delta t over m times psi naught. And that is equal to the integral dp. And just a momentum representation, that's easy. So it's psi naught of p modulus squared times e to the I p times k times delta t over m. Okay? So effectively, this is just the Fourier transform of our initial momentum probability distribution. Or inverse Fourier transform, depending on how you define that. Okay, and of course, let's just assume an initial Gaussian wave function. So we just say psi naught of p is equal to 1 over the square root 2 pi delta p, because if we know one thing, we know how to Fourier transform Gaussians. And e to the minus p minus p naught squared divided by 2 times delta p squared, and sorry, 4 pi delta p squared, because we want a Gaussian for its modulus square. So it's very easy to just Fourier transform that, and just Fourier transforming it gives rise to another Gaussian, where you basically get this delta p squared in the exponent. But because we have an expectation value, a non-vanishing expectation value, this initial momentum p naught, the initial expectation value, also enters. So I think we can just write down the solution for that. So we find the overlap operator, psi naught u2 dagger u1 psi naught is equal to e to the I delta phi, which is the laser phase difference, plus the clock phase omega atom, plus the recoil frequency times delta t. And then I've just put in the Fourier transform, and that's minus delta p squared times k squared times delta t squared divided by 2m squared plus I times p naught, the initial momentum now enters, and that's a problem, k times delta t over m. This is just a Fourier transform of that Gaussian. So we again now observe our interference signal, and we observe now that actually this expectation value has a modulus that is not equal to unity. Because of that displacement, we don't see a perfect overlap anymore, because it was an operator valued overlap operator. And then we see now that this here is a Gaussian again. And what we see is that the interference signal is now Ig is equal 1/2 1 minus or plus, sorry, plus visibility cosine phi. And we observe now the visibility and this visibility V is equal to the Gaussian, which is just, the modulus of it, that is minus delta P squared times K squared times delta T squared over 2m squared. And we observe now that, if we have a vanishing momentum distribution, our visibility is equal to 1. Why is that? Vanishing momentum distribution means that we have an, infinitely broad wave packet in space. And because we have it displaced in space, of course, the overlap will be perfect. But of course, nothing is completely delocalized in space. So as soon as we have a finite momentum width, we observe a decrease in contrast. We can also have this decrease this visibility by increasing the displacement. And because that basically just, is a parameter in delta T. Also, I saw yesterday some of those posters that were discussing, for example, gyroscopes. And they also had rotations in there. And they also looked at the loss of contrast in form of a Gaussian. And the calculation is exactly the same. It's because the lasers are rotating, not everything is overlapping, and you don't have overlapping arms, and you get a decrease in contrast. That's why you're trying to compensate that, for example, through tip-tilt mirrors. Next point, gravity gradients. If you have forces and each arm experiences a different force, also those arms will not perfectly overlap at the final beam splitter. And so gravity gradients, which means that there is a different force on each arm, which is an harmonic potential effectively. That means you have locally a different force, if you like. You also don't get a perfect overlap and a decrease in contrast. And you can counteract that by adjusting the momentum transfer. That's something that Albert Rura, also from Ulm, developed, and it was also then, of course, implemented experimentally. And so that's here now the visibility. Yes?
Well, I guess the first counteract this with changing like a delta T.
Yeah, of course, ideally you want to, yeah, exactly. But in principle, you have to calculate that and then see, okay, do they overlap? Sometimes it's not only a displacement in position, but also in momentum. And then you have to really balance that. But there are techniques and there are papers that really clearly say, okay, how can I make those wave packets overlap perfectly so that I mitigate this loss of contrast?
But any explicit dependence on Z, is this like kind of putting this under the
wait for the gravimeter, that's the next part. Okay, because we're just talking about free particles, we don't have any potentials. But the cool part is we see everything that's happening here just for this trivial example. We see this loss of contrast without going through very complicated math. I mean, it's just a Gaussian. Yes. Yes, so exactly. So the loss of contrast effectively is because you see spatial fringes. But the integrated particle number, of course, doesn't resolve those. So what Dorte is referring to is the following. I have two wave packets, and Alexander will talk about that probably, or I guess. We have two displaced wave packets, and they interfere, and they have basically here interference fringes between the two. And effectively, those interference fringes are causing this loss of contrast. I also do have a slide prepared at the very end of this lecture. Okay, good. So that's only half of the truth. We also have a phase. And now and this phase now is the following. It is again our laser phase, delta phi. And now I have this timing asymmetry omega EG plus omega K plus the Doppler shift nu K of P naught. And remember, P naught times delta T. P naught was our initial momentum. And what you observe now here is that you actually have the energy difference, not only internal energy difference, but also the kinetic energy difference between both arms for this little period of time delta T that is asymmetric. So you measure here a clock phase plus a kinetic phase, which depends on the recoil by this delta T. Two other comments. First of all, for recoil measurements, you actually want to measure something like these phases that depend on kinetic terms, because you want to measure h bar k over m. So you are designing atom interferometers that are closed, that are nonetheless susceptible to these phases. That's the first point. The second point is, okay, you would say, okay, there's a phase, I can calculate it, but this dependence on the initial position is bad. Why is it bad? Because you're running your experiment for a number of times, and if your initial position fluctuates, this phase fluctuates. So what you really want is you want your phase to be independent of all initial conditions, unless you want to measure the initial position, of course. But because there's an uncertainty to the initial position, you ideally want to get rid of that. And all of those, not only the loss of contrast is a problem, but all those, mitigation techniques try to actually overcome this problem, because they really don't like the dependence on initial position and initial momentum. Of course, our example only includes the initial momentum for now. Any questions so far? Yeah.
So, right, upper line omega 18, and we're also omega.
I'm sorry, EG, I just switched notation. It should be omega atom. Yeah. I have a different notation in my notes, and so it's inconsistent. Mm-hmm. Omega k is the recoil frequency. We introduced that yesterday as well. Omega k is h bar k squared, so it depends on the transferred momentum divided by 2m. So it is effectively the kinetic energy associated with the recoil. Okay, good. So there are a few take-home messages for this trivial example, and you can learn a lot about rotations, gravity gradients, and so on, just based on this example. Okay, good. That was the second example. The third example is a gravimeter. And as we just said, it's bad to have an open. Actually, you want to mitigate that. So let's just build it symmetric. Okay. So that also implies that we don't have any clock phase anymore or something like that. And actually, when you have constant forces, the same force on both arms, it doesn't modify this closing condition. So you can always go to a joint freely falling frame for both arms, and then it looks like the free system. We will now calculate actually the phase that arises from the Hamiltonian, and now somebody just asked the question, so what about the Z dependence? And we will include the dependence because we now have a gravimeter. So H external is equal to P squared over 2m plus mgz. Of course, at this point, we can also include next higher order moments in our gravitational field. We would call them gravity gradients. And that's just, if you Taylor expand your gravitational potential to second order, third order, fourth order, and so on and so on. But now we just keep the first order because things are easy. And of course, we come back to our friend that I actually mentioned every single lecture. Or it's actually three friends, Baker, Campbell, and Hausdorff. And so it is e to the operator x times e to the operator y is equal to the exponential of x plus y plus 1/2 times the commutator x and y plus higher orders. But actually, for us, these higher orders are not an approximation because everything actually drops out at that order. And so we don't have to worry about those. It's exact what we are doing. Okay. And again, let's write down the Hamiltonian with increased momentum. And we've done that already in some sense. So H external of Z and P plus H bar K, we just have to square the kinetic term. So we reproduce H external of Z and P, but we get two further contributions, and this is again the recoil frequency and the Doppler frequency, plus H bar omega K plus H bar nu K of P. Okay. So I guess you can all, that's fine for you now, since we squared P plus H bar K enough. Okay, now we have to calculate the overlap operator. And because now all those Hamiltonians do not commute anymore, we cannot as easily merge them into one exponential, but that's what we want to do. So we have to go through Baker-Campbell-Hausdorff. So let's have a look at the commutator. And the commutator is the following. The commutator of minus or plus I over H bar times H of Z and P times T, commuting with minus or plus I over H bar, H of Z and P plus H bar K, so this increased momentum, because that stuff also arises, times T. Delta T is equal to 0, so we don't have to worry about that. Okay. And of course, the only remaining part, H commutes with itself if it has the same arguments. So of course, I'm now, external. So it commutes with itself. So the remaining part, or what we actually have to calculate, is minus or plus I over H bar times H of external of Z and P, commuting with the recoil frequency plus the Doppler frequency. But actually, the recoil and Doppler frequency, the recoil frequency is just a scalar function. There is no operator in it. So the only remaining part is effectively just the Doppler detuning. So I have minus I or plus I over H bar times the Doppler detuning, H bar P times K over M times T. And of course, stuff drops out at this point. And what I do have to calculate now, I just get out this minus or plus I squared. I get a T squared. I divide by H bar. And now, of course, the Doppler detuning depends on momentum, so it does commute with the kinetic term. And the only term that it doesn't commute with is our potential, in this case, the gravitational potential. So what's remaining is just M times G times Z commuting with P times K over M. In this case, also the masses drop out here. And we can get out the K, so it amounts to minus, because it's the I squared, K times G times T squared divided by H bar and the commutator of Z and P. And this is, of course, the canonical commutation relation, IH bar. So we find minus I K G T squared. Okay? So the commutator of the Hamiltonian with momentum, with the Hamiltonian of increased momentum, gives rise to an additional phase that is minus kgt squared. And that is the gravitational phase that a gravimeter measures. Let's now look at our two branches. Okay, so we're looking now at U2 dagger or at U1. Their forms are still written on that board. For our case, it is now e to the, well, if it's 1, it's a negative time evolution. If it's 2, it's a positive time evolution. And then it is I times h external of z and p times t over h bar. And the second contribution is e to the, again, minus for the U1 or plus for U2, I times h external of z and p plus h bar k, sorry, plus h bar k divided by t over h bar times t over h bar. And now I just apply Baker-Campbell-Hausdorff. Oh, I don't want that. I now apply Baker-Campbell-Hausdorff. And so what we see now, Baker-Campbell-Hausdorff, is just the sum of both Hamiltonians, x plus y, plus the commutator. And so we can write this as the exponential of, again, minus or plus. And now we are having I over h bar, the Hamiltonian h external of z and p plus plus h external of z and p plus h bar k multiplied by t. And here this is, of course, all operators. So that's the first line. And now the commutator actually is independent whether it's U2 dagger or U1. So it's always minus I kgt squared over 2, because we have here in Baker-Campbell-Hausdorff a factor 1 over 2. So what we observe is that it is, oh yeah, and of course what I'm missing, I just missed that. I have e to the minus 1 and plus 2, this capital phi phase that I'm missing. And of course, that's also appearing here later. So, but this is just trivial because that's always standing there. Okay, and so now we have minus I kgt squared over 2. This is now for U1 and U2 dagger. We have exactly the same form. And just multiplying the two, now it's easy to just use Baker-Campbell-Hausdorff. And we now observe effectively for the overlap operator, because everything is now the same, we can use again Baker-Campbell-Hausdorff, but everything truncates. So the green minus sign and the blue plus sign also cancel. And the remaining part is just for the overlap operator. It's just U2 dagger times U1 is equal to e to the I delta phi minus kgt squared times the identity of the external motion. factor of 2 because we have twice kgt squared. And that's it. And now I also say there's perfect overlap. We have perfect visibility, but we get an additional phase. And this additional phase depends on gravitational acceleration. So far, any questions? I know it's a little bit messy with Baker-Kempel stuff, but that's the easiest way to get to the result. And it's only one line of calculation. Okay, so you all buy that it's gravity, it depends on gravity. And probably have seen that equation. So now, of course, we have perfect visibility and we see the interference signal. And I can't emphasize that enough. So it's IG is equal to 1/2 1 plus cosine. And now we have a phase delta phi minus kgt squared. So we now observe an interference signal that actually depends on gravity and depends on onto our interrogation time uppercase T. Yes?
So the visibility is linked to the fact that you will overlap the wave packet at the end when you close your interferometer.
Yeah, if they don't overlap perfectly, you get a decrease.
You say that if you have a gravity field, the two paths are going to possibly experience a different gravity field. But that at the end, that gives you a phase.
So it's a constant force. So let me explain that again in hand space. So you have the atoms here. You now have a beam splitter. That means the 50% of the atoms get a kick and go up. But at the same time, both of them are dropping, but they're accelerating the same. So they are doing something like that. Then this here gets a reduced momentum, and they are still dropping, but going up. Let me just draw that.
Gravity is the same for both.
Yeah, because both arms feel the same acceleration, so they actually are accelerated the same way, and that doesn't induce any difference to both arms.
But if the gravity field is locally different for both,
then of course you get a displacement, and this is for enter-reduced visibility, and that is actually caused by gravity gradients, because then you locally have something different. Or you might have a long tube, 10-meter tube, and floors and other stuff that is close by. So a local gravitational field might not be a perfect Newtonian or linear potential, but it might have higher orders. And higher orders will always lead to this effect of, first of all, not closing the interferometer. That means you get a dependence on initial conditions. That's bad. And you get a reduction of visibility. Okay, good. So interference signal, minus kgt squared. We see it's independent of the initial state now because everything is closed. It's susceptible to gravity. And we get this additional phase from the linear potential. Okay, let me now explain to you how we now can extract this phase from the interference signal. And that's also, I hinted at that yesterday. Often, and actually we saw that we had to chirp the laser to stay for each internal or transition on resonance. Often you just chirp throughout the interferometer. Yeah, that is first of all for to stay on resonance, but also to log chirping rate to acceleration. And for that, we assume now the following. We now assume that our laser phase changes. So this delta phi that we had, was this difference of 3 phases that I've written down here, phi 2 minus 2 times phi 1 plus phi naught. And we just said, okay, these are the initial phases of those pulses. Let's now write it down and just say that phi naught, phi L of pulse L is equal to just phi at time TL, and that is just some phi offset. Let's just also call it phi 0 minus omega times T plus TL, sorry, plus alpha, K times alpha times TL squared over 2. And that's exactly what we had before as well, when we were discussing the individual pulses. And we have the chirping rate. And so let's look just at this 3-point sampling. Okay, and okay, then we have 30 minutes for the, so delta phi is equal to phi 2 minus 2 times phi 1 plus phi naught. And now effectively this phi naught always drops out because it's 4 times, plus 2 minus 2 phi naught. That's fine. For the just, and we choose now, and that's of course crucial, T2 is equal to 2 times T, T1 is equal to T. And what we observe now is minus omega times 2T minus 2 times T plus 0. So this drops out. And what's remaining is plus K alpha over 2 times 4 times T squared minus 2 times T squared plus 0 squared. So this here vanishes. And all of that is just 2 times T squared. So we have a K alpha T squared. And what we now observe is that we have a phase of our interferometer, phase that is delta phi minus kgt squared, that is k times alpha minus g times t squared. Okay? And now we can also write this, as, for example, 1 minus, alpha minus g, alpha divided by g minus 1 times gt squared, for example. And what we observe now, if alpha is equal to g, the phase vanishes. So we are always at the same point. Let's now see how we find this point. And this is also the point that helps us, because the phase is periodic to pi periodic. We cannot really extract the gravitational acceleration really from it, because this 2 pi periodicity. But what we really want to find is this point where alpha is exactly equal to g. And we find this by performing the experiments. So we have here the interference pattern. And we now use different chirping rates. So we perform one experiment with one chirping rate, then go to another chirping rate, then go to another chirping rate. And what we observe is if both agree, of course, we now have this 1/2 plus cosine 1/2, and cosine is equal to 1. So we are always here. And now, of course, if we deviate, we find just an oscillation. So if we find something like that. Okay? And this is, for example, for one particular time. This is for time t1. If we now use a different time, the periodicity will differ. So we perform now the very same experiment for a different time, and we'll observe different oscillation T2. However, we see that for alpha being equal to g, both of them are maximum. And that's how we can identify this point, by just using different interrogation times and all the time chirping the experiment to find the maximum value. And that's how you would implement a gravimeter. And by that, you can read off your chirping rate, where chirping rate is equal to 1. We know what the gravity is, what the gravitational acceleration is. So we perform the experiment by tuning the chirping rate, and on top of that, using a couple of different interrogation times, and then see where all the fringes overlap. That's the zero fringe, and that's our gravitational acceleration. And we're done. I will show experimental data for that as well after the next 2-hour lecture. No, I mean, in 30 minutes or so, 20 minutes. Any questions? You're all happy with that? Okay, cool. Yes, please. I'm sorry, I can't understand you.
Very alpha a little bit.
Yes, of course, of course. But of course, it depends on, you know, I normalize this with a wave vector and so on. Of course, you only have a certain range, but you also have some idea where your gravitational acceleration is. It's probably around 9.81 or something like that, meter per second squared. So you kind of go to that and then you measure and then chirp from that point on. Yes. The 3-point sampling, that just came out. We just saw that we evaluate the laser phase at the, 3 times of the laser. That's just whenever we transfer momentum, we also imprint the phase of the laser. And the phase of the laser at that particular time depends on how it was chirped before. Yes, that's if we tune our laser frequency the way it's up there and then plug it in. Okay? Yes. Yeah, well, I mean, at that point, you're measuring optical frequencies, and then, you have all the techniques that you know from references, optical frequency references, and you can look at, frequency combs, and that can be done very precisely. Yes. No. Okay. No, within our approximation. But if you tune it too much, your atoms are not diffracted anymore, because remember yesterday, the first lecture, we said it's important to diffract the atoms. So at one point, we will not really diffract the atoms if it's too wrong. And then we do have a problem. But if it's within that range, at first, we won't see a reduction of contrast by just chirping. Yeah. Any question back there? Not anymore? Yes.
Like for the chirping,
yes.
Very accurately. Why do you not measure the RF frequency?
Yes, I mean, I'm sorry. You just have to. I mean, you basically have to measure, and in fact, it's somehow the setting of your laser or your AOM that actually is used to create the chirp. That's the setting that you're using, and that's something you know very precisely. Yes. Ask Sven. No, but I will show in the Quantus experiment. There's a very nice plot, and then you just roughly see that. I mean, it's an old yeah. Yes. No, we assume that we can basically tune those laser phases to what we want. But now you're telling, okay, what happens if I have vibration? If something happens to the laser and I can't control it, and that's bad. In that case, you would have to average over those fluctuations our signal, and then you would see a loss of contrast. Yes. No, in the open interferometer, it's just because we have a timing asymmetry that leads to an opening. But I just did that as an example. If you have, for example, quadratic potentials, if you have rotations, you will see the same effect. No, we are not compensating, but because we have a linear force, it will perfectly overlap if we have symmetric times. Just because both arms accelerated exactly the same way. And then there is no problem. You could go into a common freely falling frame, and then it's gone. Okay, good. Yes.
We have all of these phases, the laser phases,
the gravitational phases that they're shifting.
Yes.
And we make a measurement at the maximum, and we know that without the shifting, for example, and we know that we have the gravitational and laser phases, right? When we go to the maximum, we know that they are equal.
Yes. And that's what we are doing. We are checking where the laser phases are equal to the gravitational phase.
But then this phases, we know them.
We know them. Yeah. And we tune them and know them and control them. Well, you can also do optical interference effects, and you're actually using, for example, AOMs to chirp, or using whatever frequency. It's not not a huge chirp that you actually have to do. Okay, good. Now, I think, given that there's only 20 minutes, I might not be able to talk about many particles, but I want to talk about a single particle and the sensitivity. So far, we just discussed the signal of a gravimeter, and now I want to talk about sensitivity. And so, what did we do? We measured, we talked about the interference signal in one particular exit port. And I just showed to you, and I always drew something like, okay, here's our phase, here's Ig, that's the number of atoms in the port, and then we see this type of oscillation. That's fine. That's the expectation value. We said that, you know, Ig is the expectation value of the projector onto an exit port that we define through the ground state. However, I also showed to you experiments yesterday where we had the whole statistics of measurements. This is the expectation value. That means we have to average over many runs. If we have a single run, there will be a fluctuation. There is an error to it. So what we actually observe is that we not only have this expectation value, but we have, you know, we have some distribution around that with our measurements. And that distribution may depend on the phase itself. Look like that. So here, we just have fluctuations of our signal. And because of that, because we have those fluctuations, if you just see at this thing, we also have to associate that with a phase uncertainty delta phi. I'm sorry, this should be delta Ig, fluctuations. And that would be associated with a with an uncertainty of our phase in the orthogonal direction, just because everything is not unique anymore, and I just get a scattering. I showed this experimental data to you. I will do that later at the end of this lecture as well. Now, I want to infer this phase uncertainty and the fundamental phase uncertainty. So let's just characterize those fluctuations of our intensity in that exit port. And of course, let's just use the variance. So we say, so by variance, so let's say by variance. And that's delta Ig squared. Okay, good. So let's just do Gaussian error propagation, something that you learned during your first lab course or before or wherever. And so how does that work? Well, we have delta Ig squared is equal to dig, our signal derivative with respect to phi times delta phi squared times delta phi squared. So effectively, if we have a fluctuating signal, it connects through a Gaussian error propagation to a phase uncertainty. Okay, so far everybody's with me. Let's just write this as a phase uncertainty. By just dividing through by this derivative. So basically we find delta phi, sorry, the phase uncertainty, delta phi is equal to delta phi, and now I'm getting delta IG divided by modulus of IG derivative with respect to phi. So effectively, what you're doing is you're looking at the expectation value and the fluctuations of your signal at that point, and then you take the slope of your signal at that particular point and divide by that. And that's the sensitivity for delta phi. And this is just Gaussian error propagation. So we can now, of course, generalize that, but for an accelerometer, I just want to calculate the relative uncertainty. So for an accelerometer, I have phi is equal to k times alpha minus g times t squared. We just calculated that. So I can calculate now the relative uncertainty of g divided by g. And that is just yet again Gaussian error propagation. That means I just write down the phase uncertainty delta phi divided by d phi derivative dg, because that's the parameter of interest. And delta phi is just our phase fluctuations. So phase fluctuations. Divided by, and of course I have to multiply that by g, kgt squared. Okay? So that tells us our uncertainty of a gravity measurements depends on kgt squared. And actually, uncertainty, I want a very low uncertainty, so I have to make this denominator very large. And the numerator very small. Numerator very small means low phase fluctuations of our signal. And denominator large means we have to increase the momentum transfer. That's called large momentum transfer techniques. I think Jason will later on during this week talk about that. And we can increase the interrogation time. You can do that, for example, by going to 10-meter fountains, or you drop everything for 100 meters, and then you have a 100-meter free fall time to do that. You can do it on the ISS. You can do it in microgravity, or you can also relaunch the atoms. So increasing T is cool because we can increase the sensitivity. We can also work with somehow trapped systems, for example, to increase T. And we can increase the momentum transfer by increasing K. So these are the two routes to enhance the sensitivity. Plus, of course, we want to reduce phase fluctuations. Okay, good. So now let's look at the single particle phase uncertainty. And now we look at the intrinsic fluctuations. Now, of course, you have laser phase fluctuations. You might have vibrations and all of this entering the signal. I just want to show you the fundamental limit of it. And your intuition tells you also, good visibility is probably good for my signal, for my sensitivity. If I have no visibility, I can't observe anything. So that's what we are going to describe. And let's look at the intrinsic fluctuation. Now, how do we calculate those? Okay, we have our signal, and we observe that the signal is just the expectation value. So IG is just the expectation value of some type of projector onto an exit port. Yeah, this is the projector that we use to define the exit port. Yeah. And that means our projector, because that's our observable, it is idempotent. And that is actually pretty cool, because we can now say that because it's, its square is equal to the projector itself. That's the property of any projector. And that's the observable, because we took a photo of atoms at one particular position. And then we always get this property. we can now just calculate the variance. And we can calculate this variance quantum mechanically. So how do we calculate the variance? We calculate the variance by delta IG squared is equal to the square of our observable expectation value minus expectation value of our observable squared. And now because I know pi squared is equal to pi, I can just write this as the expectation value of pi minus the expectation value of pi squared, which means I can write this just as the interference signal. It's 1 minus the interference signal. And this is now a quantum mechanical fluctuation. These are quantum fluctuations of our atom. And this is the intrinsic limit that we can achieve if there is no technical noise. And now that's very easy because we have the form, the explicit form. And the explicit form is, we have 1 over 4 because it's 1/2. This here is just 1/2, 1 plus visibility cosine phi. So I have 1/4, 1 plus visibility cosine phi times 1 minus visibility cosine phi. I just plug that in, that general form we have for 2 arms. And that means we just find for the phase uncertainty delta phi squared delta phi squared is equal to 1 minus the visibility squared times cosine squared, because this is just, this is 1 over 4 times 1 minus visibility squared cosine squared. So that's just the variance divided by 1/4, so that cancels, times the visibility squared sine squared. Of course, I omitted phi. So we observe a variance that depends actually on the phase itself. And it depends on the visibility. And we can now see what happens with that. Let's just assume perfect visibility. So we don't have any overlap, but of course it gets worse when we don't have that. So let's just assume that, we have v equal to 1. And that implies delta phi squared is equal to 1 minus cosine squared phi divided by sine squared phi. And of course, sine squared is 1 minus cosine squared. That's just a trigonometric relation. And we get this intrinsic single particle phase uncertainty is equal to 1. And it's independent of the phase. That's for a perfect interferometer. However, if we have imperfect visibility, we just look now at the optimal phase. And there we just say, okay, we choose a phase where the denominator is very large. Very large implies sine is very large. Sine can be equal to 1. So we just say, okay, sine squared is equal to 1. So we just set a phase where sine squared is equal to 1. At that point, cosine squared is equal to 0 because phi is just the point of operation. That's where we want to operate our interferometer. That's at mid-fringe at pi over 2. And in this case, we find a phase uncertainty. Salah? At the phase pi over 2 that goes with 1 over v. So having imperfect visibility because clouds don't overlap makes our signal worse. Our phase uncertainty increases because v is smaller than 1, and this will be always larger than 1. And so we want a high visibility to have the best sensitivity. Now, of course, you can operate also at other points, not the working point, but that, of course, is now not, that, of course, also will give you a phase uncertainty, but maybe not the optimal if you have loss and if you have an imperfect visibility. Yes? Yes, phase uncertainty would be 1 radian, but this is only for a single particle. Now, if you don't care for lunch, we could also go through many particles, but you're laughing, so you're happy with that. I will come back to this when we have many particles, just to give you an overview. Yes, please. Yeah, then you're okay. Yeah, so exactly. Then you would be, of course. Yes. Of course, that would be an unfortunate phase. In principle, you can also think about a constant phase offset that you induce, for example, and then also work with that. You could also, for example, exactly. So what you do is usually you work at alpha equal to g, then apply an offset by pi over 2, measure at that point, and then you measure, for example, how precise can I go for that? That's what you would do in that case. Because you have control over the laser phases. Yes? Okay. Could you just, I mean, you have a signal. I will show that to you. Let's come back to that when I show my slides. I just want to finish up for multi-particles. So if you now have many particles, and you can also do a quantum derivation of that, and let's assume that those particles are uncorrelated and not entangled. That makes a difference. You can effectively show that your overall sensitivity decreases by a factor of the number of particles. Many. In this case, we could perform the same. I could write down projectors. I've written down projectors down here to present those to you. In principle, we can write down a projector for each and every atom, do the very same calculation just using an n particle state. And in that case, you know, having n particles, one will observe that delta phi at the optimal value, or delta phi many particles, is equal to 1 over the square root of n times delta phi of the single particle. And this is called shot noise. For entangled particles, you get around that. You can get around that, but it's very difficult to do that. But if you just have an ensemble of n atoms, your overall phase sensitivity drops. And I could write down a projector and do the very same calculation. It's not that different. And so what we now observe for that overall, for example, for a gravity measurement, we find something like delta G over G, which is the relative uncertainty. And we observe that this scales with 1 over the square root number of particles times the visibility times kgt squared. So we want a lot of atoms That's why we want to optimize those sources, and Wolf did, you know, I guess in every lab you're trying to optimize those number of particles. We want a good visibility and a closed interferometer. We want large momentum transfer, and we want a large interrogation time. And on top of that, instead of having independent uncorrelated particles, we could also have uncorrelated runs of the experiment. So we can enhance that by repeating the measurement a number of times, and then we get yet another scaling with the square root of the number of runs. Okay, I promised you some slides and some experiments. And I don't want to break that promise. Okay, open interferometers, that's what we discussed first. Now I got it. We said that the divisibility, this is what we calculated, is determined by the overlap. And here I plotted, or I think Alex plotted the visibility as a function of your momentum, initial momentum width, and the timing asymmetry. And if there's no timing asymmetry and a very, very narrow momentum width, you have a lot of overlap in position space. You have a good visibility. But as soon as you have a different timing asymmetry, you basically drop in your visibility. And of course, for a finite momentum width, you also get that problem. The reason is the following, and this is actually how those, I showed this figure, how those fringes were generated. This is actually just by inducing a timing asymmetry, so you get spatial fringes in one shot. Spatial fringes implies that you don't have, you know, they are also pi phase shifted, but you cannot transfer, integrate over them. You will not get up to 1 because there's always the spatial fringes cut out. So you cannot go, by integrating over those atoms, you cannot go to unity. And by that, you will never get perfect visibility. So spatial fringes imply a displacement and an imperfect visibility for the integrated particle number. You can see that here. If this is the cloud that you're using, and you have a spatial fringe that is very broad, you basically see oscillations of almost all the population between here and here. However, if you have very narrow fringes, fringes that are smaller than the width of your wave packet, you can make a pi phase shift, and in your other exit part, you never will observe the whole population because there's always a residual population that doesn't appear here. It always has to show up here. And that leads to a loss of contrast, to a decreased contrast. Coming to this null fringe thing, this here is actually accelerating our light field in terms of meter per second squared. And we now perform for 2 different capital T's, 5 milliseconds, 3 milliseconds, 1 milliseconds, different runs, and scan the trapping rate. And what we observe now is that these red dots, the blue dots, and the black dots all coincide. And that's actually how we infer the local gravitational acceleration in such an experiment. This is what I just said, just in nice, because here are a lot of data points, and data points can be very ugly. Phase uncertainty. I showed this interference scan again, and this is multiple runs. You have number of atoms, and you see this is the distribution for one specific phase setting. And this is fluctuating. And this is what I just said. Okay, this is the intensity fluctuation. So I have one phase setting. I don't change anything, but I see a fluctuation in population. And this is actually the fluctuation that we just calculated as a variance of our intensity. And we see that this depends on the phase. So here it's larger, here it's smaller, here it's again larger. And this is actually what's coming out of the calculation that we just did. And now, looking at this phase difference, you know, if I have such a big spread and I measure something, you know, if this is the uncertainty, I could also just transfer it to this delta phi in the other direction, because an uncertainty in the intensity implies, through Gaussian error propagation, an uncertainty in the phase. And that means intensity fluctuations imply, and I observe here intensity fluctuations imply an uncertainty in the phase. Now, this here is an experiment that was performed using now entanglement. And in this point, you also observe for different phases, you see here a different distribution of the intensities that you measure, and they can get very small. And yeah, exactly here, you see now that you can actually go below this shot noise limit if you use entangled particles. And finally, we talked about the sensitivity. This is the sensitivity. I already showed to you, this is just increasing the momentum. So there are a lot of works that say, okay, we want to increase the momentum. I yesterday saw a poster where people said, okay, we can go to 600 h/k. You always have to be a little careful if that's throughout the interferometer or something like that. But let's say hundreds of momentum transfer can be done. So you enhance your momentum transfer by a factor of 100. This here would be using single photon transitions and always imparting more momentum or sequentially more momentum on one arm. Yeah, and this is using, for example, Bloch oscillations to even further separate those. There's also a poster on Bloch oscillations. And then, of course, the other thing is you can now go, for example, to large fountains, 10-meter fountains, where you increase the time. You can relaunch your atoms. So this is within 1 centimeter, but when they drop out of your chamber, you can just give it a kick so that they are relaunched. You can use, we have seen rings and guiding potential. You can use guiding to just increase the time where you perform your interferometer. That also will enhance the sensitivity. And you can go to microgravity. This is the drop tower where people drop 100-meter something and they have 4.5 seconds of free fall time, or even a catapult with 9 seconds. Going to, parabola flights that was by the French Space Agency. Here, the German collaboration that shot up the Marius rocket, 6 minutes of microgravity. And this here is the CAL project, where people are doing experiments with atom interferometers in space. So actually, that atoms drop out of our interaction region is not a problem anymore, and we can scale up the time, and by that, the sensitivity of our measurement. If there are any questions, I'm already over time. Feel free to just drop by afterwards. Otherwise, I'm done for today. It was a pleasure giving 3 lectures, and Alex will continue this legacy with episode number 4 and 5, The Empire Strikes Back. And so, yeah, so thanks.
For announcement, please hang your poster.